I'm going to be showing you guys a different version of the chain rule than what we did in the first time. So this was the original chain rule. Now a simpler version of this is just when you have a function within a function. So I would like to represent it sort of as, let's say, how do I write it? So let's say I have a function. I'm going to use different colors over here. So I have a function, I have a function, I have a function within a function. Let's say this is within something. Wait, I'm going to change the color scheme over here. I have a function, but within a function, and you need to differentiate this. You need to differentiate this. What you do is just you basically just differentiate this thing. Oops, differentiate this thing, and multiply it with the differentiation of the inner function. You may be like, well, what is this weird notation that you've just written out over here? We don't even understand this. Just give me a second. I'll make it make sense in just a second. So this is the different version of the chain rule that's much easier to use. How this works is, let's take an example over here. Let's say you have this thing y equals 2x plus 10 whole squared. Now what you need to sort of understand over here is that you have two functions. One of the functions is the outer one. I'm just going to draw it over here. This is the outer function. And all of this guy over here, all of this thing inside of this, that's the inner function. That's where this guy comes in. Okay, and so you have this equation for y, and you want to find how y changes with respect to x. So you say, okay, dy with respect to dx, and so you got the same thing on this side, dy dx, and it has all of this stuff in it, which is 2x plus 10 raised to the power 2. So what you're doing is essentially you're trying to differentiate all of this stuff. And of course you can go ahead and use the other version of the chain rule for it, but that's way lengthier and it's way messier. This guy is way easier. And how you do it is, well, basically the key lies in identifying your outer function and your inner function. So I did that over here. I was like this whole power thing, this entire stuff in red. That's my outer function, and then that outer function has some inner function. And I have this thing, this outer function and inner function thingy, and they want me to differentiate it. So all of this is basically this stuff. All of this is basically this stuff. And what they want me to do is they want me to differentiate this stuff. So how do I differentiate a case where I have a function that's within a function? And well, that's what I tell you over here. So when you have a function within a function and you're trying to differentiate it, I'll just write differentiate. You're trying to differentiate. What you need to do is you need to take the differentiation of the outer function. So you can see the triangle, the outer function, it has this prime on it, this dash on it. What that means is you differentiate this outer function and you don't do anything to the inner function. You see it doesn't have any dashes on it. And then what you do is you multiply this entire thing with the differentiation of the inner function. So I'll just show you guys what that looks in real time. So this right over here was my outer function. That stuff in there was my inner function. And I'm supposed to differentiate all of this. So how do I do it? Well, I differentiate the outer function first. So I differentiate all of this stuff in red first. And imagine if this bracket, imagine for a second, just ignore all of this junk inside of it. Just look at the bracket. The bracket has a power. Now, how would you differentiate an x with a power? You just use the power rule, right? That's exactly what you do over here. So what you're going to do is you're basically going to apply the power rule over here. I'm going to have this 2 over here, this bracket, and then from that power, I'm going to subtract 1. So that's what I do. I differentiate the outer function first. And then I don't do anything to the inner function, so I just write it as it is. And once I have this entire thing set up, now I sort of need to multiply it. I need to multiply it with the differentiation of the inner functions, of the blue stuff. And the blue stuff is basically 2x plus 10. So what do you get when you differentiate all of this blue stuff? So I'm just going to make it a little simple for you. That constant, whenever you have a constant and there's no variable next to it, the differentiation of a constant is always going to be 0. That constant could be 3/2, it could be 1000, it could be pi, it could be negative 19, it could be anything. If it's a constant, if it's just a number, it differentiates to just 0. If you don't believe me, go ahead and try and differentiate this. And I explained this in the previous video why this thing would give you 0. So go ahead and do that. Now, this constant term, that's just, if I differentiate it, it's just going to be 0. What about this 2x over here? So we have 2x, and that x is raised to the power 1. So if I'm trying to differentiate it, what you can do is you can sort of ignore that 2 for now, just look at this x raised to the power 1. And it's just going to be 1x, 1 minus 1, and all of this is going to be multiplying with that 2. So this is just that this 1 and minus 1 is just going to cancel out. It's going to become a 0. This is going to become a 1. And all of this bracket is just going to give you a 1. And this 1 multiplied by this 2 is just going to give you 2. So the differentiation of the inner bracket is just 2. So you multiply that guy over here. Now what you're going to get is you're just simply, when you solve this out, you're simply just going to get 4. And you are going to get 2x plus 10 in here. Now this is all of the chain rule that you've applied. If you don't believe me, if you don't believe that these two chain rules, don't believe that these two guys don't look anything alike, go ahead and apply this chain rule on this same question, and you will get this result at the end. Okay, so having done this one sort of example, let's check out these other examples that we have written on the side. So we have this other example, which is 2x squared plus 5x raised to the power 2. And you can see over here that even over here you sort of have this outer function, and then within that function there's this inner function. So what you want to do is you want to differentiate the outer function first. So that's just going to be 2 bracket, and then when you subtract 1 from that power, it's going to give you 1. And then you are going to put the insides of it just the way they are, and you're going to multiply it with the differentiation of the inner function. So I'm not going to do it all over here, but I'm just going to speed this up a bit. So this is just going to be 4x plus 5. You're going to multiply this entire thing with 4x plus 5. That's going to give you your answer. And so we can go ahead, we can do that over here for our second example. The second example basically has this under root. So this under root now becomes the outer function, and then inside of it you have this 9x plus 3. So what you do is you basically differentiate the outer function first, and you're like, how do I differentiate a third? How do I differentiate a square root? Well, a square root is basically a power of 1 by 2, right? So all you're doing is you're differentiating that power of 1 by 2. It's going to be 1 by 2, and when you minus 1 from this, you're just going to be left with minus 1 by 2. And inside of this, you're going to have 9x plus 3, and then you're going to multiply all of this with the differentiation of this bracket, and so that's the insides over here, and so that's just going to give you 9. So you solve all of this thing, and that's going to be your answer. And so we got our last example over here, which looks a little bit tricky. It's this 47. It's 47 over cube root x raised to the power 3 minus 1. So how do I differentiate this thing? This thing looks way complex. Now, again, what I want to do over here is I can sort of see that this guy right here would sort of be my inner function, all of this guy right here. And this cube root 3 is going to be sort of the outer function. Now, why am I not concerned with this 47 or this fraction? Well, because they're not variables, right? If I'm solving them, I'm sort of differentiating the variables. I'm not differentiating numbers. I'm not doing anything with the other stuff. So I'm not really concerned about that. I'm concerned about what I have over here. And what I have over here, this guy looks sort of like a function within a function. That's why I'm sort of just putting my focus on this guy. So now what I'm going to do is I'm first of all going to try and break this guy over here, this double function. I'm going to break it free from this fraction. Now, one way I'm going to do that is I'm first going to get rid of this cube root first. And I can convert the cube root into this power of 1 by 3. And then what I can do is, again, I'm trying to liberate this guy from this fraction. So one way of doing that is, well, by just writing this differently, and one way of writing this thing differently would be to say 47 multiplied by 1 over this entire thing, x to the power 3 minus 1. And now what I can sort of do is I can send this combined function up there to the numerator, because we do not differentiate in the denominators. We take our differentiations into the numerator. So once we do that, we will be left with 47. And the power is going to change its sign. So if it's positive 1 by 3, it's going to be negative 1 by 3. And it has all of this stuff, x to the power 3 minus 1. And sort of all of this stuff that I've done so far, it's not even differentiation. It's just algebraic manipulations, making this thing algebra ready. My bad. Making this thing differentiation ready. Once it's differentiation ready, then we can actually go ahead and start the process. So now is where I actually start the chain rule. Let's start the chain rule. I say I have an outer function and I have an inner function. So what I can do is I'm just going to sort of ignore this 47 right now, because that 47 is a constant. I'm just going to sort of ignore it right now. I'm just going to sort of look at this thing over here, this guy over here. So it's this thing right over here. This is the same as, let's say, if you had 47 multiplied with x raised to the power negative 1 by 3. How would you differentiate it? But first, ignore this 47 and solve out this x. That's what we're trying to do over here. We got this function over here. We're trying to sort of ignore this 47, and we're just sort of trying to look at our function. So what we're going to do is we're just going to look at our function, and we have this power over it. So how would you deal with that power over here on this side? And you would just sort of take it over here down here and multiply it with that x. That's exactly what I'm going to do over here. That power is going to come down. It's going to multiply with this function. Oops, in the wrong colors. And then first of all, what I'm going to do is I'm going to subtract 1 from this power, and then the inner function is just going to be the way it is. And I'm still, that 47 is going to multiply with these guys, but I'm not really concerned with that 47 right now. But I didn't do one step, right? I still have to multiply all of this stuff with the differentiation of the inner part as well. So what I'm going to do is I'm just going to find out what the differentiation of the inner part is going to be. I'm going to do it fast. It's going to be differentiate all of this. You're just going to get 3x raised to the power 2. You're going to multiply all of this with 3x raised to the power 2. And then you're going to multiply these guys, all of this, and then once you get your answer, you're going to multiply this 47 with that answer. So that's how you do this. So this chain rule, you can use this chain rule or this chain rule for when things get tricky. But ideally what you're trying to look for is okay, do I have a function that looks something like this? And if you do, then this right over here is how you differentiate that sort of function.